Hi friends, till the last class we have discussed about Latimer diagram, which was one of the simplest representation of electrode potential of any redox couple for a given element. Today we have to deal about Frost diagram. It is actually a graphical representation of Latimer diagram. It is a useful representation of redox potential data. Actually, this data we are collecting from Latimer diagram of the corresponding elements. Stability of various oxidation number of element can also be studied using this diagram. Oxidizing and reducing nature can be combined. From this graph, we can do many more applications. It is actually a plot of delta G0 against oxidation number. This is our equation. Here we are actually plotting n E0 against n. N E0 against n, where n is the oxidation number. Here we have to multiply number of oxidation number with E0. Actually, n E0 is minus delta G0 by F. Now we are coming to the construction of Frost diagram of various elements. We are doing it in detail for manganese and oxygen. Additionally, you will be provided with the diagram of nitrogen also. In examination, no element is mentioned in syllabus, so you can expect any element in examination. First, we are starting with Frost diagram for manganese. To start with Frost diagram, first of all, you should have an idea about the redox potential, which is actually available from the corresponding Latimer diagram. So, consider the Latimer diagram for manganese in acidic medium. Later, we have to see the Latimer diagram for manganese in basic medium also. Both can be recorded in a graph. This is the Latimer diagram for manganese in acidic medium. Here manganese can exist in +7, +6, +4, +3, +2 and 0 oxidation state. 0, 2, 3, 4, not 5 but 6 and 7. These are the various possible oxidation state of manganese in acidic medium. The corresponding reduction potential or electrode potential of each couple is given in diagram. These are the corresponding values. These values can be converted to Frost diagram as follows. This is the diagram for manganese again in acidic medium. For our convenience, that diagram in the previous slide is pasted here also. This is not a separate diagram. In order to get the required data, we have to start with a table. In first column, you can see oxidation number. Second column, you have species. Oxidation number are 0, 2, 3, 4, 6 and 7. Respectively, for species manganese Mn2 plus, Mn3 plus, MnO2, MnO4 2 minus, that means manganate, then permanganate. Now we have to calculate Ne0. You have to do the calculation in this column and answer can be written on the last column. Here oxidation number is 0, N is 0. So 0 into anything is 0. So value here is 0. Then for Mn2 plus transition, Mn2 plus change in oxidation number is 2. So N is 2 into corresponding potential is minus 1.18. Then you will get minus 2.36 volt. Then for conversion Mn to Mn3 plus, for the conversion of Mn to Mn3 plus, to become Mn3 plus, first Mn needs to be changed into Mn2 plus, then to Mn3 plus. So it is a two-step. So the first transition from Mn to Mn2 plus value is already here, minus 2.36, plus for this change 2 plus to 3 plus, then N is 1 into corresponding potential is 1.51. Then you will get minus 0.85. Then Mn to MnO2, that is a three-step process, Mn to Mn2 plus, Mn2 plus to Mn3 plus, Mn3 plus to MnO2. But for the first two changes, total value is present here. So you have to write it minus 0.85. So we have reached Mn3 plus. Now we consider last change, 3 plus to 4 plus. Again 1 electron change into corresponding potential is 0.95. Here you can see the value. Then you will get plus 0.1. Now 0.1 plus for this change, again 1 electron change or 2 electron change, that is 2 electron change, 4 to 6. So it is 2 electron change. Therefore 2 into potential is 2.09. And totally you will get 2.19. No 2.19. Here you have 2 into 2.09. So the value is 4.28. Again 4.28 plus 1 electron change into potential is 0.89. So you will get 5.17. Actually our graph is between N and N is 0. First column and last column. This is the graph. How to plot it? In x-axis you have N, means oxidation number. Possible oxidation numbers 0, 1, 2, 3, 4, 5, 6 and 7. Here you have N is 0 along the x-axis, y-axis. At first, For zero oxidation state, Ne 0 is 0. So you have to mark here. Where you can mark? Here you can mark. The next one is for oxidation number 2. For oxidation number 2, you have minus 2.36. Minus 2.36. That you can see here. Minus 2.36 is around here. Not minus 2. Minus 2.36. In third, you have plus 3 and minus 0.85. 4 plus 3. 4 plus 3. Where is plus 3? This is plus 3 oxidation number. For this plus 3, you can plot here minus 8.5. That is here. Then for plus 4, it is 0.1. For plus 4, it is around 0.1, approximately here. For plus 6, you have here. Sorry, for plus 5 there is no point. For plus 6, you have the value 4.28. 4.28 approximately here. And for plus 7, it is 5.17. 5.17 around. Using a scale, you can connect these lines. This is the Frost diagram for manganese in acidic medium. Okay. Now we will see basic medium. In basic medium, we have MnO4 minus plus 7, manganate plus 6, plus 5, plus 4, plus 3, plus 2 and 0. First column N, that means oxidation number, last column N is 0. We are doing the calculations. Normally for 0 oxidation number value is 0. For Mn to Mn2 plus, change is 2 into potential is minus 1.56. Then you will get minus 3.12. Then minus 3.12 plus again 1 electron change. 1 into potential is minus 0.234. Minus not 0.234. It is 2.34. You have to correct it. Minus 2.34. Then you will get minus 5.46 as the N is 0. Then minus 5.46 plus again 1 electron change into potential is 0.146 here. Then you will get minus 5.314. Similarly, for next change, plus 4 to plus 5, the existing value of 5.314 plus 1 electron change into 0.93, then you will get minus 4.389. Then minus 4.389 plus 1 into 0.27, then minus 4.114, minus 4.114 plus 1 into 0.56, this value, then you will get minus 3.554. Here you can see all the N0 values are negative, but in previous case we had only 2 negative values, other values were positive. So this graph can also be plotted in the previous one. In basic medium, 0 oxidation number, it is 0, then minus 3.12, minus 5.546, minus 5.314 likely. So you will get points like here 0 here, then 4, 5, 6, 7. All the values are negative end. This is the frost diagram for manganese in basic medium. One more thing you have to add in this graph is writing the species. It is manganese Mn2 plus, this is Mn3 plus, this is MnO2, this is MnO4 2 minus, this is MnO4 minus. Here it is Mn, here it is Mn2 plus, then Mn3 plus, MnO2. Likely you have to write the species for other points also. With this we completed the Latimer, no, not Latimer diagram, frost diagram for manganese. Now you have to see the frost diagram for frost diagram for nitrogen. It is Latimer diagram in acidic medium and it is for Latimer diagram in basic medium. As we have done for manganese, you do it for nitrogen also. The corresponding values you have in Latimer diagram, you can easily convert it into a graphical form, which we can call it as frost diagram. So you can calculate n is 0 for different n's. What are different values? 5, 4, 3, 2, 1, 0, then minus 1, minus 2, minus 3. These are the possible oxidation number for nitrogen. I think it is higher than the oxidation number feasible for manganese. So you will get a graph like this. In acidic medium, you will get a graph which is represented by this red line. Similarly, for basic medium, you will get graph just shown by the blue lines. Red line is at pH 0, that is acidic, pH is 14 basic, which is actually shown by red lines, sorry, blue lines. Now you have to go for frost diagram for oxygen. For that purpose, you are now provided with Latimer diagram for oxygen. Oxygen can have mainly 3 oxidation numbers, 0, minus 1 and minus 2. In superoxides, they have minus half, but that is not shown here. Here we are considering 3 oxidation numbers which are common, 0, minus 1 and minus 2. 0 in oxygen, minus 1 in peroxide H2O2, and in water it is minus 2. Here you have to take it as 1.76, not 1 comma, 1.76. Here it is 0.68. This is obtained from the skip potential calculation. This is for acidic medium and this is for basic medium. Correspondingly, you are doing the conversion and you will get the frost diagram like this. You can try for drawing this diagram with your own calculation. This is one of the simplest frost diagram which you have, so you can expect it in exam also. Nitrogen is highly complicated one. As compared to nitrogen and manganese, it is somewhat simpler one. This simple diagram need to be studied well. Then characteristics or applications of Frost diagram. In the initial stage itself, we have predicted that Frost diagram is capable to predict the oxidizing and reducing nature of various species of elements in various medium or at different pH. Slope of the line joining any two points in a Frost diagram is equal to E0 of the couple formed by the two species that line represent. That means in this diagram, if you find the slope of this line, that is y by x, then you will get electrode potential of this couple. If you find slope of this line, you will get reduction potential or electrode potential of this couple. Which couple? H2O2 bar H2, H2O2 bar H2. That is the first statement. For example, in diagram for oxygen, E0 H2O2 bar H2O. E0 H2O2 bar H2O can be calculated from the slope of the line representing that two species. Slope means y by x, then n E0 by n. See here. Consider this couple H2O2 bar H2O. Here you have to calculate n E0 by n, delta n E0 by delta n. N E0 for H2O2 will be here. It is around minus 0.7, around 0.7, and for H2O it is minus 2.34, I think, minus 2.46. So for N E0 minus 0.7, where is this is minus 0.7 minus 2.46, this is the value, minus 2.46 by change in oxidation number. For H2O2 it is minus 1 and water it is minus 2. So you will get minus 2 here and minus 1 here. So minus 1 minus 2, minus of minus will plus, then you will get 1.76 as the potential. This is true in Latimer diagram also, 1.76 volt. For nitrogen, NO and N2O, 3.1 minus 2.41. NO means nitrogen is plus 2, here it is plus 1. So difference is 2 minus 1 for nitrogen, N2O and NO. This is the line. You have to find the slope. Here it is 3 point and here it is 1 point. Actual value is 3.1 and 2.41. Then you will get the value 1.59, which is the value in Latimer diagram for the couple NO bar N2O. This is first application of Frost diagram for calculating E0 of a couple from the slope of the line joining that two species. Second application is in Frost diagram, if you have a line with positive slope like this, then species on the top will be a good oxidizing agent towards the species on the left. As the slope of the line increases, oxidizing power of this species towards this species will be high. Oxidizing power of species at the top will be higher towards or for oxidizing the species on the left. In the same way, if you have a line with a negative slope, then species on the top will be a reducing agent towards species at the bottom or species at the right. So, in this kind of diagram, here you have oxidizing agent. It can oxidize this species. If you have this kind of a diagram, this is a reducing agent and reduce the species at the bottom. For example, you have to check the frost diagram for manganese. In this diagram, in acidic medium, you can see positive slope from Mn2 plus to MnO4 2 minus, from this region to this region. So, all these are oxidizing agents towards the species at the bottom. So, we can say that MnO4 minus, that is permanganate, is the strongest reducing agent in this diagram because it is at the topmost position of a line having positive slope. MnO4 minus is a good oxidizing agent towards other species. It is an oxidizing agent towards this species. So, better oxidizing agent is MnO4 minus because it is at the top of the line having positive slope. In the same way, consider this line which has a negative slope. In this negative slope, manganese is here and manganese 2 plus is here. So, manganese will be a good reducing agent towards Mn2 plus. It is a good reducing agent towards Mn2 plus. That is the point which we have cleared here. You have to write down the notes for these two lines also. Next application of frost diagram is the prediction of stability of the species. In Latimer diagram, instability can be seen when the reduction potential on the right hand side is greater than left side and they undergo disproportionation. The same thing can be seen in this diagram also. If you have a frost diagram with lines like this, so this species is above the line connecting neighboring species. So, it is unstable and disproportionate to this one and this one. If you have a Latimer diagram frost diagram like this, below the line connecting two species, then these two species both are unstable. They can come proportionate to this one. So, we can say that a species in the frost diagram is unstable with respect to disproportionation like this. If the point lies above the line connecting two adjacent species, ഇവരെ കണക്ട് ചെയ്യുന്ന ലൈനിൻ്റെ മുകളിലാണ് ഇയാളെങ്കിൽ ഇയാൾ അൺസ്റ്റേബിൾ ആണ്. ഡെഫിനറ്റ്ലി ദേ അണ്ടർഗോ disproportionation to the neighboring two. And example can be seen in Frost diagram for oxygen. See, in oxygen, in diagram for oxygen, and now it is clean, you can check the position of H2O and O2. By connecting them, you have to draw a line. Okay. Then H2O2 is above that line. So H2O2 is unstable and disproportionate to O2 and H2O. That reaction you have seen. H2O2 is an unstable compound. It disproportionate as 2H2O plus O2. That phenomenon can be explained using Frost diagram very easily from the position of H2O2. In the same way, the species co-proportionate to a single species or one species that lies below the line connecting to this species and this species are placed above the these two species jointly form a line and we have a species below it. For this species it is stable and these two are unstable, so they are proportionate to this one. For example, in basic medium of manganese, Mn2 plus and Mn2O3. Mn2 plus and Mn4 plus. Mn4 is this one, Mn2 is this one. By connecting these two points, you can see a point below it. So these two species are unstable and they co-proportionate to this Mn3 plus. This is the example for co-proportionation. So totally we have discussed 4 applications for Frost diagram. First one, oxidizing and reducing nature can be predicted from the slope of the line and position of the species. If a species is present at the top of a line having positive slope, then that species will be an oxidizing agent towards any other species below it. And if you have a line with negative slope and species at the top will be a reducing agent. That is second application. Then we have discussed disproportionation and co-proportionation also. With this we completing Frost diagram. Thank you.